Alright, so this video is going to be on the preparation of alcohols, ethers, and epoxides. Remember, epoxides are just a cyclic ether. Um, so these are going to be done with SN2 reactions, okay? And we already know this stuff, so awesome for us, right? Because it's more or less a review, but with a little bit of kind of just a different look of it, right? So we already know how to make alcohols, right? Primary alkyl halide with a hydroxide, boom. Using a methoxide instead of hydroxide, you can make an ether. This is an unsymmetrical ether, and this would be a ethyl methyl ether. Okay, ethyl, remember we put in alphabetical order, just name each substituent, add ether on the end, right? And then of course the top one is ethanol. So, of course there are drawbacks to this approach in making the alcohol and the ether. And so again, we already know about these drawbacks, right? So we do know that hydroxide is a strong base as well as a strong nucleophile. So E2 is going to be a competing reaction, okay? And then we'll have, what that means is that we'll have alkene byproducts. And if we're trying to make an alcohol or an ether, that's not ideal, right? Sorry, let me just give you this. It's pretty much the same thing with the methoxide, right? So, or alkoxides in general, right? So that an alkoxide, remember, is an OR group instead of like an OMe or OET. And these are also strong bases. And so we're going to get that E2 competing reaction and therefore alkene byproducts. But there are ways around this, right? And so the best outcome for this particular reaction is if we're going to have a methyl or a primary alkyl halide, right? Or an alkyl group. I say alkyl group because we can have any leaving group, and I want to make that a very obvious to you. So this leaving group doesn't have to be a halide, right? It doesn't have to be X. It could be a variety of things. We've seen the list of good leaving groups, right? So substitute that in for that, okay? And so, yes, again, best outcome for this particular reaction to make an alcohol or ether is going to be with a methyl or primary alkyl group with a good leaving group. So to make that ether, we have the Williamson ether synthesis. So we have this ethyl methyl ether. If we move back, so remember this is our retrosynthesis arrow. It's like an equal sign with like a greater than less than look. We can make it with this chloroethane and methoxide, okay? Or we could actually, if you think about it, do it with ethoxide instead of methoxide, and then swap the halogen to the methyl group, so it's chloromethane, okay? Now, one thing we want to take a look at is this is a primary alkyl halide, the chloroethane, right? And then this chloromethane is a methyl alkyl halide. So that methyl alkyl halide, well, just remember there are rates of reactivity for SN2 reactions, right? The trend. So if we go from methyl to primary to secondary to tertiary, we have methyl as the fastest reaction, and then tertiary not occurring for SN2 specifically, right? And so that means the best outcome for making this particular ether is using the methyl alkyl halide. So the chloromethane route would be the best because the rates of reactivity are faster, and you're also going to eliminate the possibility, especially in this case, of having that E2 competing reaction, because there's not even you can't even have an E2 elimination on methyl alkyl halide, okay? So let's see another example of this. Basically, the goal in these particular reactions is when you have Williamson ether synthesis gives you two options to make the ether, and you want to choose the best one, which is the one with the less substituted alkyl halide, or the alkyl group with the leaving group, because that means the SN2 reaction is going to be faster, okay? So as you can see for this one, if you cleave on either side of that oxygen in the ether, you can kind of put the oxygen on one side or the other, and then kind of substitute in a halide or a leaving group and then that's how you break up your molecule in order to separate into two pieces that would be viable sources for preparation of an ether. Okay, so it might take some practice, but really what we have here is this. You can also double check your work, right? So have the nucleophile attack and then see if you get the ether, right? That'll help you identify whether or not you put maybe accidentally put an extra carbon in or something. And then we can see we have a primary alkyl halide on this one. This is the better route because the other is a secondary alkyl halide and it's a slower reaction. Okay, so um, we have these two alkoxides, right? So that is another important factor of the Williamson ether synthesis. So how do we make those? Well, we can just kind of have those as a source, right? We could just throw in this isopropanoxide or like ethoxide or methoxide. You see that often with like sodium cations or whatever. Um, but the way you make it is, let's say we have an alcohol, right? And then we throw in a base. We drop that base. All right. So then what the purpose of that base is, uh, obviously to remove that acidic proton on the alcohol, right? So um, this is an acidic proton, which means if we have a strong enough base, we can remove it, and that would give us our alkoxide. So here are some examples. We have sodium hydride and sodium amide. Those are really strong bases, like uber strong. And so those are some super common ones. Sodium hydride is actually the most common, probably, just because it's a great source, especially in the lab. It's really easy to use. You just throw it on top, and it's you can filter it off, and the H2 gas is a byproduct, and so H2 gas just kind of leaves as a gas, and it's no problem. You don't have to purify it, is what I mean, or isolate it from any byproducts, really. Um, Obviously, sodium amide is super strong as well. It's going to undergo basically the same mechanism. You remove that proton, and then you move on. So you might think, okay, so what about hydroxides? Hydroxides will work also, but the pKa of alcohols is around 16. The pKa of water as a byproduct is around 15.7, which is pretty much 16, which means that you're going to have an equilibrium. Okay, and so you're not really going to have an abundance of that alkoxide present, and so this isn't really the best option to go. Okay, it's not a great option. So again, the best one, the most common one you might see, like sodium hydride, because again that H2 gas leaves and it's perfect, and it's definitely never going to be in equilibrium because um, the gas left, right? One of the products left, so you can't go back. So you might see it like that or above the arrow. Um, Either way, and what you get again is this cyclohexanol turning into this oxide, sodium cation, H2 gas. I'll typically just draw the alkoxide. I won't really draw the other byproducts as often, but know they are there, know they exist. And then the ether synthesis like this. It's that's pretty straightforward. We already know alkoxides are strong nucleophiles, and we know how to do SN2. So this is some easy stuff. You guys are stoked about this because it's not really anything new. Okay. Now this one's kind of fancy, right? What if we had this setup right here? We have a secondary alkyl halide. We got a non-nucleophilic strong base. So we're not going to get an SN2 reaction on that bromine or the alkyl bromide position with the base, right? But so what is a base going to do? A super strong base is going to swoop on a proton. So swoop on, anytime you see a strong base, grab the most acidic proton, draw that product out, and then look to see what can happen. The only thing we can do now with this is an intermediate because it's really reactive. Um, and let me just draw this out for you real quick. We have this alkoxide. We have a secondary alkyl halide. I mean, what is the recipe? What are we making, right? If you got cheese and you got bread and some butter, you're probably going to make some grilled cheese. If you got this alkoxide and an alkyl halide right next to each other, you're probably going to make an epoxide. That's really all it is. So It's an intramolecular reaction because it reacts with itself. I love intramolecular reactions. Um, they're really interesting, but they're also just kind of fun to make, right? Or fun to recognize, especially. And they're super fast because they're always in close proximity of one another. They're always going to be right next to each other, ready to collide. And as long as they have enough energy to do so, they will. And that's how you make an epoxide. It's just at least one example. All right, so let's go over the reactivity of these alcohols and epoxides or ethers. Basically, this is a really strained angle. It's, remember we talked about it, it's 60 degrees and it wants to really be 109 degrees. So that's obviously highly strained. A nucleophile can come along, it could be weak or strong, and attack one of those carbons, and that pops open the ring. It busts it open, and then you get the nucleophile substituting for that oxygen, and then the oxygen pretty much just creates an alkoxide. Okay, and this is pretty much all we can do with that epoxides. It gets a little bit more complicated when we talk about stereochemistry, but we'll get there. So, alcohols reacting with nucleophiles. The hydroxide is a poor leaving group, right? So that's not going to happen as an SN2 reaction right off the bat. The strong nucleophiles are strong bases, and so what's likely going to happen is you're going to form the alkoxide, and then by removing that proton, right? And so that's not something that you would probably want to do. Um, so if you wanted to substitute that OH group, what you need to do is make that OH a better leaving group, okay? And we do know how to do this, whether we know it or not, or whether we're aware of it. If because we know that OH, if you give that another proton, and then it's forming water, right? We know that water is a great leaving group. So if we have some strong acid, I'm not going to be explicit yet, that OH, that oxygen is basic, and so it grabs that proton, forming this oxonium ion. This is a trivalent oxygen, and it's a great leaving group. Water can leave. And now we can start doing different reactions with it, right? What does this look like? It looks like a cyclohexane with a leaving group on it. And so what kind of reactions do we know how to do with this? We know how to do an elimination reaction, and we know how to do a substitution reaction. Again, this is stuff we've already seen, so you should be excited because you know this already. Bye.